Okay, welcome back to Principles and Properties of Magnetism, Part 3. Okay, Principles and Properties of Magnetism, Part 3 by Terence Payne. Okay. Here we're just looking at the question in regards to the question of question 11. And it's asking you to calculate the current flowing. Okay. Now again, let's begin to look and see what we can do here. And here we have reluctance S. And we're going into a different area now, basically. The ratio magnetomotive force. The ratio magnetomotive force to total flux is termed the reluctance of the magnetic circuit. S represents reluctance, okay? Now, do I need to move this over? But can I get everything into place? Yeah, I can. The finger can see everything into place, yeah. Okay. Now I don't want this here to be out of view in any way, okay? Must be able to be seen. So it's size 10. So let me see if I can make this a little bit larger. Okay, make it probably 16. Okay, yeah. Okay, and this here must now be much larger. There's no question about its function. Okay, there we are. Okay, and now here is the examples that's been done for you. You must work out these examples, you must write them out, you must work them out yourself. But some of you just think you could do it from the screen, but it's not. This is not your work, this is my work, okay? Therefore, you need to be doing it, your own work for yourselves, okay? Okay. So let me look at this now, and let me make sure that I can bring this up to, just bring this up to a bit. Bear with me for a second. I don't want to bring it up too far. No, that's good enough. I think I don't want to take it out of my boundary framework. Okay, let's make sure we get this in. 14. Okay. And this up as well. Now here you've been asked to calculate the reluctance of a 200 turn coil wound on a wooden former having a mean circumference of 0.6 meters and a uniform cross-sectional area of 0.05 square meter. Okay, for a non-magnetic former, S equals L over mu O. Now remember, should be common L. Now I just write that in for my own reference, okay? But it should be common L, but I thought it's important to emphasize that L factor, okay? Okay, let me just go back to this. Okay, and we'll take the page from the top. Okay, now I've read that over to you. Now here, you need to look at exercise and do the exercise. Extract the information from the question, okay? Always. Now, question 3 continues. Okay, I have no idea why I've put question 3 continues. Hang on, I'm gonna miss something. No. An iron ring having a mean circumference of 1.25 meters and a cross sectional area of 1,500 millimeters square is wound with 400 turns of wire. Okay, question 3, I don't know why that says continue, but that's life. Must have put it there for a reason at the time. 4, okay, let's look at this. Sorry, oh sorry about that. I was just trying to move this thing around. Mm-hmm. 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 Okay, let me just go back to the top a little bit, show that I've got this in play. Okay. Now these questions are for you to do. Ignore question 3 continues. I must have put it there for a reason when there was an overlap on my screen. Okay. And again, this is part 3 of yes, I wrote this work and it was to remind me as to what I was doing on a certain day. It's okay. When you get to my age, you need all the reminding you can get. Okay, let me just look at this. And again, we're looking at part 3, principles and properties of magnetism. Okay? That's a bit odd. Now, what I have here is these are for you to do at your own exercises. look back at the work that's been done, okay, already. And here what I've now done is to give a further explanation as to magnetizing force. So here I've looked at magnetizing curves for ferromagnetic materials, okay. The relation, well, I would say the relationship between the magnetizing field H and the magnetic field B can also be expressed as the magnetic permeability of mu equal B over H, or the relative permeability mu R equals mu over mu O, where mu O is the vacuum permeability. That is the vacuum, you got no air in a vacuum, it's empty. The permeability of ferromagnetic materials is not constant, but depends on H. In saturable materials, the relative permeability increases with H to a maximum, then as it approaches saturation, inverts and decreases towards 1. No, this is 15, am I on 15? I'm on page 15. 1 second, bear with me for a second. I don't want to go over beyond the given page. Okay, so let me just make sure I can. Okay, yes I can. I think I can do that. Yeah. Okay, let me just bring you up. Can I push you up? 1 second, bear with me for a second. Let me just bring this up. They must, okay. I brought it into a, bear with me for a second. I was talking, my computer is off over onto the other table, you see. So I've got to, I'm trying to do this. Now let me see if I can, if it's in my interest to, I've got to deal with this in a different way now, because yes, I'm going to look at this in a different way, because I've got a lot of here. What page am I on now? I'm on, yes, 15. Okay. Okay, let me do something different and bring this down, because I'm going to need to extend you. Okay. Okay, it's okay. I'm just trying to make sure that I'm looking at this from a correct perspective and that it's easy to read. So at the moment I'm going to have to expand some of this text, make it larger, which is going to run me into the next page, which I didn't really want to be doing. But let's get it done anyway. I'm going to go with font size 16. Okay. Let me break it up a little bit as well. Okay. Making it easier. The idea here is to make it easier to read. Okay. It is very important that it is easy to read. Very important. Okay, some parts may not be as easy as I would like. Let's see what we can do with that. Okay. Okay, let me bring in some. Okay. Either here. I'm hoping that that will show up brighter and more effective. Okay, that's my hope. I don't know if it's going to work or not. Okay, yes, I can go to you, I think. And I can make you change color to you. Bring you here. Okay. Oh, sorry. Drop me down, yep. Okay. Okay, I will, yes, let me just, I made you bigger. So happy with that. Okay, let's bring you down to here. Down to blue. Make you bold, okay? Okay. Now I'm going to bring the hysteresis loop further down so that I don't have to once again. Okay, bring you on today, and go back to you for a second. Let me just bring you up to scratch. Okay, and let me go back up a little bit now to begin to bring you into a given explanation. Okay. Now ignore that from Monday, whatever, because that was just me planning ahead of what I was going to be doing. Magnetizing coils for ferromagnetic materials. The relationship between the magnetizing field H and the magnetic field B can also be expressed as the magnetic permeability mu equals B over H, or the relative permeability mu R equals mu over mu O, where mu O is the vacuum permeability. The permeability of ferromagnetic materials is not constant, but depends on H. In saturable materials, the relative permeability increases with H to a maximum. Then as it approaches saturation, inverts and decreases towards 1. Different okay. Sorry, I'll just try and check something here. Different materials have different saturation levels. For example, high permeability iron alloys used in transformers reach magnetic saturation at 1.6 to 2.2 teslas T, whereas ferrites saturate at 0.2 to 0.5 teslas. Some amorphous alloys saturate at 1.2 to 1.3 teslas. Ferromagnetic materials like iron that show saturation are composed of microscopic regions called magnetic domains that act like tiny permanent magnets that can change the direction of magnetization. Before an external magnetic field is applied to the material, the domains are oriented in random directions. The tiny magnetic fields point in random directions and cancel each other out. So the material has no overall net magnetic field. When an external magnetizing field H is applied to the material, it penetrates the material and aligns the domains, causing their tiny magnetic fields to turn and align parallel to the external field, adding together to create a large magnetic field B, which extends out from the material. This is called magnetization. The stronger the external magnetic field, the more the domains align. Saturation occurs when practically all the domains are lined up, so further increases in applied field can't cause further alignment of the domains. It means that it reaches a point of saturation. This is there. It's not going to go any further. Okay. This is part 3 of principles and properties of magnetism. Okay, and I would allow you to take note of this and make notes for yourselves. Okay, thank you. I hope you found this useful. Bye for now. Bye bye. Okay, let me just run up, make sure that I've got everything in place, and I didn't miss anything when I was talking and blubbering. Okay, thank you. All right, I hope you found this useful. Have a good day. Bye bye.